Hey everyone, welcome back, and today let's solve Leetcode problem 2981 titled Find Longest Special Substring that Occurs Thrice. So we're given a string S that consists of lowercase English characters, and a string is called special if it's made up of only a single character. So for example, the string ABC is not special because it actually does have duplicate, or rather not duplicate, but unique characters that are more than one, right? We have one A, another B, another C. It's not only made up of one single character, so it's not special, but the strings D, 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 Z, Z, and F are special because there's only one character in each of their strings, right? We only have one character of D here, one character of Z here, and one character of F here, so they're considered to be special strings. So we need to return the length of the longest special substring of S, which occurs at least thrice. But if no special substring occurs at least thrice in our input string S, we have to output -1. And they actually also define what a substring actually is. It's defined to be a contiguous, non-empty sequence of characters within a string, so it's similar to some sequences. However, it actually has to be contiguous, right? Our elements have to be consecutive. So in example 1, we have our input string S to be 4 A's and our output to be 2. The reason why is because the longest special substring that actually does occur thrice in our input string S is 2 A's, AA, right? We can choose these 2 A's, these 2 A's, and these 2 A's. AA itself is actually special, and it does have a frequency of at least 3. Again, these 2 A's, these 2 A's, and these 2 A's, right? And that is actually the maximal length achievable for a special substring in our input string S that does have a frequency that's greater than or equal to 3. So in example 2, we have our input string S to be A, B, C, D, E, F, and in this case, we have to output -1, because although we do have special substrings like the A individually, the B individually, and so on and so forth, none of these substrings actually have an occurrence greater than or equal to 3. In fact, every single one of these special substrings only occur once. It's just that letter itself in its corresponding index, right? A doesn't have a frequency greater than or equal to 3, all of it is a special substring itself, and so for that reason, applying that same logic to all the other individual substring or special characters, we have to output -1. And finally, in example 3, we have our input string S to be ABCABA, and in this case, we have to output 1, because the longest special substring that actually has a frequency of 3 in our input string S is only one character. That's the maximal length we can actually achieve. And in this case, it's simply an individual A, right? A itself is, of course, a special substring because it only is one character itself. And it also, in this case, does have a frequency of 3, which is obviously greater than or equal to 3. We can use this A, and this A. So with those examples out of the way, I will give you guys a few seconds. You're going to just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so sorry about that, guys. I realized that I was talking a little bit too fast. I'll try to slow down for the coding and explanation for this part of this video. So, the way we can actually solve this problem efficiently, believe it or not, is actually to use binary search, right? One of the most fundamental concepts and algorithms for data structures and algorithms, right? And we're going to actually use the binary search algorithm to determine the longest valid substring and its corresponding length. Right? And we're going to actually have a helper function to do this, to help us rather, and we're going to use this helper function to actually implement a sliding window algorithm, right? And we're going to use this to validate, well, does a current substring actually satisfy our conditions, right? Of the given length, does it actually occur more than or equal to 3 times? Right? And we're going to actually use a hash map or an array to actually count the substrings and their corresponding occurrences or frequency efficiently as we actually apply our binary search algorithm. So with that out of the way, let's go ahead and dive straight into the code here. So I'm actually going to directly define my helper function here. I'm just going to call it check for simplicity, and it's actually going to take in one parameter. It's going to take in a parameter x. This is simply the name of our current substring. And for any of you guys who are watching this video and who are using statically typed languages like Java or C++, I'm going to type in this for you guys. So x is going to be type int, and it's going to, or rather, this function is going to output a boolean. Okay. So again, this is simply going to help us verify, well, does the substring of length x, does it actually appear at least 3 times in our string? So now let's actually initialize our count here. So I'm just going to call it CNT, and it's going to be equal to a default dictionary like we talked about before. This hash map that actually helps us store every single substring and its corresponding frequency, right? So it's going to be a default dict. I just realized I spelled it completely wrong. Default. I actually don't know how to. Okay, I think it's default. Default. Okay, that should be right. And it's going to be of int, right? our keys are going to have a data type of an int, right? And again, this is simply going to help us count the occurrences or the frequency of all the different substrings based on their lengths, right? And it's going to actually provide us quick insertion and retrieval, right? Or lookup time, because again, hash maps actually do have a big O of 1 or a constant time lookup time. That's why one of the reasons why they're so important. Now let's actually initialize I, basically our index or our starting pointer, to actually help us iterate over our input string, or rather our parameter string x. Okay, so now while I is strictly less than n, we have to actually increment j to I plus 1, or rather initialize a to be I plus 1, right? And while j is inbound, so less than n, and s at that index j, while it's actually equal to s at that index I, we can actually increment our j pointer by 1. Now you may be confused on what in the world this actually means. Well, we're simply just traversing the string while our 2 pointers I, or rather indices I and j, are actually in bounds, right? And for every character s at index I, we need to find the longest segment of the same character, which is going to be s at I up until the jth index, right? Or rather s, and this is going to be, let's let me actually comment this, s from I until j, right? And these are our 2 indices, right? We're just basically finding the longest segment of the same character. So while they're actually equal to each other, we can actually expand our window, right? And once we've actually done this, we want to set count at s at I to be incremented, so plus equals in Python, the maximum of 0, j minus I minus x plus 1, right? But what is this really weird looking computation here? Well, notice how j and I is simply going to give us our window length. It's simply just the difference between our 2 pointers, and x is actually the length of our input string s, right? So effectively we're saying for every segment that we actually find, we have to add its contribution to our hash map count at index s at I if it's actually at least x in length, right? So we have to actually add it if it's at least x in length to the count of its character in this hash map, right? So count at s at I plus equals the maximum of 0 and j minus I minus x plus 1, right? And once we've done that, we want to actually set I to be equal to j. We want to simply just move or update our ith pointer to the next unmatched character, right? And simply just continuing on the search. And effectively, once we're outside of this while loop here, we simply have to return the maximum of all the different values in our count hash map, so count.values in Python, if it's greater than or equal to 3. Effectively, this is just a pretty simple way of checking, well, if any of the characters, obviously we want to use the maximum to make sure that it's kind of like the bottleneck, if any of the characters actually does have a count of substrings that's greater than or equal to 3, that means we can actually return true. This is actually a valid substring of this length x, right? It does actually have an occurrence that's greater than or equal to 3, right? Thrice, as how it is in the problem. Now let's actually start to apply our binary search. So I'm going to initialize n to be equal to the length of our input string s, and initialize my 2 pointers L and R like I usually do for binary search to be equal to 0 and n, right? This is simply the search range for our binary search algorithm. So now, while L, this is pretty standard here for binary search, while L is in bounds or strictly less than our right pointer, we want to initialize the middle index to be the sum of the 2 pointers divided by 2, right? This is simply going to be L plus R plus 1, integer divided by 2 to get that actual true middle value, right? We're simply just performing this binary search and initializing the middle point, right, which is going to represent the current length that we actually have to check using our check helper function. That's the whole point why we actually coded this up. So once we've actually initialized mid, well, if check at mid is actually true, meaning it actually does have an occurrence greater than or equal to 3, we want to set L to be mid. We want to increment L to be the middle index and search in the right position, or right half. However, if check at mid is false, it does not have an occurrence of 3, we want to set R and update that to be mid minus 1, going to the left half, right? But what does this really mean? Well, if the check function, if it actually confirms a valid substring of length mid, right, where again mid is our parameter x here, If that's the case, we want to move our lower bound up, check for the right half, which is simply just updating L. However, if that's not the case, we have to actually reduce our upper bound, which we can actually convert or control with our R or right pointer, right? And once we're actually done with this binary search, we simply have to return L, but we can only return our left L bound or pointer if it's actually greater than or 0. If that's not the case, we have to return -1. So we're really just saying here, after we're done actually applying and computing all the different computations of binary search to our input string S, we have to return the maximum valid length L if we actually updated it, if we actually found it to be greater than 0. If that was not the case, we have to return -1 because no valid substring actually would exist. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. Let's see. I might not have internet. We'll check that when we need to. Okay, anyways. So while that's actually submitting, let me actually explain how this algorithm actually works and the kind of core of the way it works. So for a quick high-level rundown, how does this algorithm actually work here? Well, we're simply actually using binary search to actually efficiently find the longest length of any special substring, right? And we're actually leveraging the monotonic property, right? Which is that a longer substring requires shorter substrings to actually exist. And by using this, we simply have to reduce the problem space insanely, right? We're reducing the problem space to go all the way down to logarithmically, right? That's literally the core main function and goal of the binary search algorithm. It's a logarithmic algorithm, right? And this helper check function actually just efficiently determines, well, does the substring parameter of this current specific length x, well, does it actually satisfy the conditions using the sliding window algorithm, using our 2 pointers I and j, does it actually occur at least thrice? So, and we're simply just doing this using our sliding window and our hash map data structures. So for the runtime complexity, this is going to be a big O of n log n solution, right? N times log n, that is. And the reason why is because, of course, binary search is a big O of log n. It's a logarithmic algorithm to actually traverse our input string s. It's log n, where n is the length of our input string s. However, the sliding window traversal of our actual input string s here, or rather our substring of length x in our check function, well, that sliding window traversal is going to be a linear time operation, right? It's big O of n. So the overall time complexity is big O of n times the log n, which is big O of n log n. And for the space complexity, the hash map and the check function, well, it's only going to, at most, use 26 characters, right? Because we know we're only limited to lowercase English letters. It's not even uppercase. We don't even have 52. We only have 26 possible chances at most of lowercase English letters to put in our hash map. So for that reason, it's going to be a big O of 1 solution, right? We only have a fixed limited amount of characters that we can potentially add to our count hash map. And so for that reason, this is going to be a constant time or big O of 1 memory space complexity solution. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.